Hello guys, today in this video we are going to discuss about formation of energy bands. So as we know, the energy of the bound electron is quantized, okay, and only discrete values of electron energy are allowed. So if you remember, we have already done this in one of the videos where we have considered this simple mathematical model of infinite potential well. So similarly, when the electron is bound, and then its energy will also be discrete, right? The wave function of this bound electron, we have already discussed in one of the videos. You can refer to that. The energy, as you can see here, the energy is, you can see En is proportional to n square here. Okay, you can see this n square here, and the wave function is also dependent on n. So these specific values of n clearly shows that the values are discrete, right? The wave function is discrete, and the energy for different state, right, different level is discrete, right? Okay. So what is radial probability density, as we have already discussed in the wave function, and the square of the wave function, which gives you the probability density, that is probability of finding the electron in a particular state, right? So probability density here, when we said the radial probability density for the electron gives the probability of finding the electron at a particular distance from the nucleus, right? And it shows that the electron is not localized, okay, at a given radius. So if you will plot the probability density versus the distance, okay, that is we said the distance from the nucleus, right? Then the graph actually shows this way, where this a0 is known as the Bohr's radius, and in the ionization and ionizing energy, we have already derived this in one of the videos. You can refer to that. The value of this A0, the Bohr radius, is found to be 0.529 angstrom, right? So this is known as the Bohr radius. Okay. So particularly this figure shows the radial probability density function for the lowest electron energy state, okay, of the single non-interacting hydrogen atom. So for a non-interacting hydrogen atom, if you will see, okay, single electron energy state, then this is what is the diagram, okay. So we said PR is the radial probability density function, R is the distance from the nucleus, and this graph actually represents, okay. Now two atoms that are in close proximity to each other. So what happens here, you can see the probability density for two atoms, like single electron atoms or hydrogen atoms, you can see, right, probability density versus the distance, right? Now what will happen when they are in close proximity, you can see, right? So the probability density curve, you can see they are overlapping with each other, right? So now what will happen to the wave function in this case, when they are like, two atoms are very close to each other, and the probability density, okay, is actually overlapping for both the atoms. The wave function, if you will see, like, the wave function that represents the electron, right? That if you'll see for individual electrons, like we have, I have shown you psi1 and psi2, right? And x is the distance. Then when they are close enough, then they will also start interacting with each other. Okay, so the wave function of the two atom electron overlaps. Okay, that means the two electrons will interact, right? So when the two atoms are very close to each other, the electrons will also start interacting. As a result, the wave function will also be overlapping, as you can see in this particular diagram. Okay, then what that interaction will lead to, right? This interaction results in discrete quantized energy level. Okay, the discrete quantized energy level, as I showed you in this in the first slide itself, right? Here you can see the energy is discrete. So if I will substitute n is equal to 1, then we will have a particular value of energy. So that's why we said it's the discrete energy value, right? Now in that discrete energy, what will happen to that discrete energy here? Okay, when these two electrons are interacting and very close to each other, then the discrete quantized energy level will split into two discrete energy levels, as you can see. So this was the discrete energy levels. Now you can see it is splitted into two discrete energy levels again, right? So this is for n is equal to 1. Suppose we have shown n is equal to 1, right? And now you got for n is equal to 1, the same energy level, discrete energy level, has splitted into two, right? So this is how the electron will interact when the wave functions are overlapping or the atoms are taken very close. Now, if we start with a regular periodic arrangement of such atoms, like hydrogen type atoms that are initially very far apart, and begin pushing the atoms together, taking them closer, right? The initial quantized energy level, as you can see, okay, will split into a band of discrete energy levels. So band of discrete energy levels, you can see. So now it is splitted. So this will happen when more number of atoms will be taken closer or pushed together, right? So what will happen? The electrons will start interacting, the wave function will start overlapping, and that initial discrete energy level will now split into a band of discrete energy levels. So what is this R0 here? R0 is the equilibrium interatomic distance in the crystal, right? So beyond this, or at this particular point R0, you can see the the energy bands, right? The splitted energy bands. Okay. Now, at the equilibrium interatomic distance, there is a band of allowed energies, but within the allowed band, the energies are at discrete levels. That is what is important. We can see they are splitted and they are discrete energy levels. So here in between, you can see there is a gap here, right? There is a gap. There is a gap here. There is a gap here, right? So there are no energy values there, right? So again, it is splitted into discrete energy level. The one energy level here is getting splitted into many energy levels. Okay. So we will discuss more about this. You giving one, taking one reference or one example, right? So now let us see what is Pauli's exclusion principle. Pauli's exclusion principle states that the joining of atoms to form a system or a crystal does not change or does not alter the total number of quantum states regardless of size. However, since no two electrons can have the same quantum number, as you can see from the picture, right? 1s2, 2s2. Now you can see 2p has got three states. So now you can see how the electron is occupying, you can, this is allowed. You can say the green tick. Okay, here this is also allowed in different states, right? But here you can see in 2p, you can see here you can see one up and one down. So here this is not allowed, right? And also you can see here two states are empty, and here you can see both the electrons are occupying up and down like states. So this is also not allowed, right? So this is what the Pauli exclusion principle, we all know that. So since no two electrons can have the same quantum number, the discrete energy must split into a band of energies, so in order that each electron can occupy a distinct quantum state. So that's the reason actually when we take the atoms very close to each other, okay, that particular discrete energy level, okay, the electrons will be actually occupying or overlapping what wave function, okay, will give you that there is a non-zero probability of finding one electron in both the states, like the psi1 and psi2, right? So it is not possible as per Pauli exclusion principle, right? It says that there can't be identical quantum states. So the energy, discrete energy level has to what be divided or splitted, right? So that's what we said. Now, uh, so in general, if you'll see, the splitting of energy levels that we discussed, suppose we will consider a regular periodic arrangement of atoms in which each atom contains more than one electron, right? Each atom contains more than one electron. Suppose the atom in this imaginary crystal contains electron up to n is equal to 3, n equals to 3 energy level. Okay, suppose we will consider if you'll consider a regular periodic arrangement of atoms, okay, in which each atom suppose contains more than one electron, right? So now suppose the atom in this imaginary crystal that we considered contains electrons up to n equals to 3 energy level. Okay, so n equals to 3 energy level, suppose we consider. Now if the when the atoms are really far apart, okay, the electrons of these atoms will not interact, right, and will occupy the discrete energy levels. They are discrete, particular discrete energy levels. Now if these atoms are brought close together, okay, the outermost electrons that is there in the n equals to 3 or n is 3 energy shell, okay, will now begin to interact initially. So when we will take the atoms closer, the outer one, the n equals to 3 energy shell, will actually start interacting first, right? So this discrete energy level now will split into a band of allowed energies, right? So if the atoms continue to move closer together, the electrons in the n equals to 2 shell now may begin to interact, okay, and will also split into a band of allowed energies. And then finally, if the atoms become sufficiently close together, the innermost electrons, that is in the n equals to 1 level, also may interact, okay, so that this energy level may also split into band of allowed energies. So if you'll see this r0, which is the equilibrium interatomic distance, right? So beyond that, you can see how when the distance actually keeps on increasing, here you can see, okay, it started splitting at this distance. Then for n equals to 2, you can see it started so getting splitted here. And then here you can see after the interatomic separation, equilibrium interatomic separation, after this you can see that there is a splitting, right? So this particular diagram that you can see, okay, is what it's actually what the splitting of the discrete energy level shown qualitatively, right, for an imaginary crystal where we consider that n equals to 3 energy levels, and how they will be interacting with each other when the atoms will be close together, taken closer, and the discrete energy level like n equals to 3, 2 and 1 gradually will be splitted into many discrete energy levels, which will actually form a band, right? Now let us see what happens in case of a silicon, in case of silicon, a group 4 a element, okay, if you'll consider. So now what overall what we discussed, like as isolated atoms are brought together to form a solid, okay, various interactions occur between the neighboring atoms, okay. The forces of attraction and repulsion between the atoms, okay, will find a balance, okay, at a particular interatomic spacing for the crystal, right? That r0 value we said, right? So in the process, important changes may occur in the electron energy level configuration, and those changes result in the varied electrical properties of solids, okay. So this formation of bands actually will define many electrical properties of solids, right? Now let us consider the case of silicon. As we know, silicon 14, you can see the electronic configuration. We can see here 1s2, 2s2, 2p6, 3s2, 3p2. This is the electronic configuration. So here you can see n equals to 3. This is the outer shell, and then you can see um, s orbital can have 2, so all 2 electrons are here, and 3p6 actually. So 3p6, but you got 2 electrons here. So this way we can consider. So in the outermost shell or valence shell, n equals to 3, and there are two 3s and 2p electrons. Okay, they will interact. Okay, when many silicon atoms will be taken together and closer, then what will happen? These two electrons in the 3s and 2 electrons in the 3p will interact with each other, and they will form 4 hybridized sp3 electrons, which we will discuss later how the hybridization occurs, okay. But 4 hybridized sp3 electrons, okay, when these atoms are brought closer together, okay, this will happen, right? Okay, now what will happen, as we have already done, the wave functions for individual atoms will now start overlapping with each other or interacting with each other, right? Now what we can do is we can solve the Schrodinger equation for such an interacting system. Okay, the composite two electron wave functions, okay, like here we showed. Similarly, many other electrons will also interact when the silicon atom is close together, right? And we call this as linear combinations of the individual atomic orbitals, or we call it as LCAO. We call it as LCAO. So L is linear, C is combinations of the individual atomic orbitals. Okay, so we can solve the Schrodinger equation for these interacting wave functions, okay, to find the final wave function, to solve the final wave function that will represent the state or the of the electron, right? When the atoms are brought closer, okay, when the atoms are brought closer, the application of the Pauli exclusion principle becomes very, very important. And we know what is the Pauli exclusion principle. As you can see, Pauli exclusion principle, this is very, very important. When two atoms are completely isolated from each other, okay, there is no interaction of the electron wave functions that we have already discussed, right? Okay, they can have their identical electronic structures, right? As the spacing between the two atoms becomes smaller, electron wave function will start overlapping, right? Now the exclusion principle says that no two electrons in a given interacting system may have the same quantum state. Okay, thus there must be at most one electron per level. Okay, after there is a splitting of the discrete energy levels of the isolated atoms into new levels, okay, which will be, I mean, which is what belong to the pair rather than to individual atoms, right? So this is what I mean we mean by exclusion principle, we have already discussed. Okay, now in a solid, many atoms are brought together so that the split energy levels form continuous bands of energies. Okay, now let us see for the silicon, in case of silicon, how the energy level splitting will happen and the band will be formed, right? So now each isolated silicon atom has an electronic structure. The electronic structure already we have discussed. This is 1s2, 2s2, 2p6, 3s2 and 3p2, as you can see here, the electronic configuration over here, okay, in the ground state. If you consider n atoms, if you consider n atoms, okay, there will be 2n, you can see 2n, 2n, 6n, 2n and 2n, right, electrons, right? But if you'll see the states, then you can see 2n, 2n, 6n, here 3s 2n, but here you will have 6n states, right? So 6n outer, here we can have 6n states, right? For n number of atoms, right? States of type 1s, 2s, 2p, 3s, 3p respectively, as we said. Okay, as the interatomic space decreases, the energy levels split into bands. This is what we discussed for a generalized case. Beginning with the outer, that is n is equal to 3 shell. Okay, as the 3s and 3p band, 3s and 3p bands, okay, come closer, okay, they merge into a single band composed of a mixture of energy levels. Okay, this band of 3s 3p levels, now if you'll see the diagram here, so what we said, we have 3p over here, we have 3s over here, right? Now here if you'll say 3s, for n levels we have 2n states, 3 and 2n electrons filled, right? Now in 3p we have actually, in the from the electronic configuration we saw that 3p2, so 2n electrons are there, so you can see 2n electrons, and p can have actually 6n state for n number of atoms, capital N atoms, so 6n states, so this is for 3n level again. Okay, so this is what we got. Now what will happen, This band of 3s 3p levels contain 8n available states. So 6n here, and this is 2n. So 8n states are available actually, right? As the distance between the atoms approaches the equilibrium interatomic spacing, that we said, that A0 value, okay, or R0, here you can see this R0, okay, R0 value of silicon, this band splits into two bands separated by an energy gap. If you can see the energy gap over here, right? Now this band, the whole band here, you can see 3s and 3p now is getting divided into two bands, you can see. Okay, this one is one band, right, known as the conduction band, you can see here, conduction band, and this is the other band which is known as the valence band. And the gap here, you can see this gap here in between the conduction band and valence band is the forbidden gap, okay, or the energy gap, right? The upper band, as we said, the conduction band, it will have 4n electrons, you can see that 4n electrons. Now it is getting splitted, total 8n states. Now 8n states, the conduction band will have 4n states here, okay. And the lower band also will have 4n states. Here you can see 4n states over here in the valence band as well, right? So total 8n states will be splitted into two bands, upper band conduction band, lower band is valence band, okay. So thus, apart from the low-lying and tightly bound core levels, the silicon crystal has two bands of available energy levels separated by an energy gap, EG, or the forbidden gap we said, which contains no allowed energy levels, okay, for the electrons to be occupied, right? And this gap, as I told you, is known as the forbidden gap, since in a perfect crystal it contains no electronic states, okay, so we call it the forbidden band, okay, forbidden band, okay. So now what happened here, we had actually 6n and 2n, so 8n states. Now you can see there is a splitting of the bands, so create, you got this 4n states over here and 4n states over here in the conduction band. Now total electrons actually in, if you'll see in the outer, like n equals to 3, you got 2n and 2n, so 4n electrons are there. So now what will happen, all these, this gap you can see filled with electrons, you can see that gray region here. So this is the 4n number of electrons. All these 4n electrons will now be here, which is the filled levels, or known as the valence band. So all 4n you got, and this one you got completely empty, which is the conduction band, okay, which is conduction band, right? So this is band theory of solids, and more we have already discussed, like at 0 Kelvin, this is the ideal condition, 0 Kelvin, where the electron will not gain enough energy to move to the, or jump to the conduction band, and that will be completely empty, and your valence band will be completely filled. And this is how the 8n states is getting divided to 4n and 4n, and all the available electrons, that is 4n electrons, will be occupied in the valence band, right? The field levels. So here the simplest representation of this band theory of solid, you can see here, this is the empty level, which is the conduction band. So we put two lines, like a band. So this is completely empty, there are no electrons here, right? Only 4n electronic states are there, which can be occupied by the electrons. Similarly here 4n states are there, but it is all filled with electrons at 0 Kelvin, as we have already discussed. And this is the gap, which is the forbidden gap. So this picture here, the schematic diagram actually is a simple representation of the band theory of solids, or it clearly shows how the energy level in silicon is getting splitted, and the how the band is formed. uh, Hope you understood this. Thank you so much.